डियर स्टूडेंट्स, वेलकम टू PHY467। आज हम पढ़ेंगे बोस आइंस्टाइन स्टैटिस्टिक्स। सो इट डील्स विद पार्टिकल्स with integer spin. So it includes a lot many different types of particles. So our scheme will be we'll start with the study of uh, bosons or Bose particles with some mass m. Later on, so it may include some gases, liquid helium, say for example, and so on. But later we will move to the massless bosons. So they include photons, phonons, and magnons. And you need to remember that the different quantizations result in these kinds of particles. So for example, the quantization of electromagnetic field gives us photons, and for this kind of field we say that we can study somehow the a gas of free photons and later we can study the Planck's law of radiation, and the sub branch is the black body distribution. So these are all quantum effects that we will try to address, and also for the crystalline materials, the quantization of crystalline lattice vibrations they gave us the phonons. Why they are important? So the phonon theory, the phonons help us understand the heat capacity of solids at low temperature. In a similar fashion, the quantization of spin waves, the spin waves are somehow the deviations of local magnetization. So the spin waves are basically deviation of local magnetization with respect to thermodynamic magnetization or the bulk magnetization. Thermodynamic magnetization means somehow bulk magnetization. So this gives us phonons, magnons. And this happens where? In a ferromagnetic material. In a ferromagnetic material, or in a ferromagnetic state of a material. So these are really interesting aspects. Photons, phonons, and magnons. So they actually somehow sum up everything inside solid state physics that we need to know about these. But we will study these things later. We have to start somewhere, and we start with the statistics only. So we start with simple Bose Einstein statistics. So Bose Einstein statistics, we have to start in the same fashion that we did for the case of fermions. So initially we have to write the partition function, the grand partition function, and then later we can calculate this probability distribution, this occupancy number, or Bose Einstein probability distribution from that. So initially we start from the same old grand partition function. So it was the grand partition function. I write it like this. So it is basically a double sum. So it is a sum over particles and sum over energy. So we write it like this. Beta epsilon 2 minus mu n2 and so on. It depends on the number of particles in the nth state. So it can be actually rearranged in somehow better format. So we can write it as like this. Sorry, this summation is over n. So this is the another method to write this same partition function. So this is the product operator pi, which is actually operating on jth states, and this is the summation. So we have to separate these exponential, which are actually multiplying with one another in form of this product symbol, product operator you can call it. So you call this equation 1. So now if we look at the term inside this square bracket, this term, this is a summation, so we write it e to the power minus beta epsilon j minus mu n. And remember that in case of bosons, there is no restriction over how many number of particles we can introduce inside a single particle state. So we can write this as, for the first state when we put 0 we get 1, and then subsequently we get with simple E j minus mu, and then its power increases minus 2 beta epsilon j minus mu and plus so on if we open this summation. And we can write it like this: 1 plus e to the power minus beta e j minus mu plus e to the power minus beta e j minus mu, everything squared and so on. So it becomes a kind of geometric series. So we have a geometric series of the form 1 plus x squared so on, and this geometric series actually can be summed to some finite number 1 over 1 minus x, provided we have a condition that the subsequent terms become smaller and smaller. So we say that this summation is only possible when successive terms become smaller and smaller. And when this is possible, so we must have, for this case, in our case here, if you see, so in this case, for every term to be smaller than the previous one, so this thing should be greater than 0 or positive. So we write, for this to happen, beta times epsilon minus mu should be a positive number. That's the condition. So in that condition we get simply 1 over 1 minus e to the power this is only special condition. Otherwise, if it does not happen, we cannot sum this series and we cannot get this result. Okay, we will see what are the implications of this result, but for the time being we just keep it like this and we proceed with our calculations, and later we will come back to this situation where we will see what happens when this term becomes smaller or greater or negative or positive. So we will see that later. So we just put this value back into 1, so we get and now we take the log of both sides. So what log does to this product operator, it converts this into a summation function or summation operator, and the rest of the things remain like that. So we write it like this. So now when we have the log of our grand partition function in this form, we have to do another approximation here. We need to use the expansion of log. It says that the expansion of log is log of 1 minus x can be expanded as this series provided x is smaller than 1. This is the condition. So this we can use for this this expansion here inside this summation. So we write, and we can ignore the square and higher terms. Okay, we first call this equation or equation 2. And then do the expansion inside equation 2. So we get and then I explain you why I did this, why it is small. This is our log of the partition function. I call it equation 3, and now we discussed the reason why we said that this can be done in the first case. So the reason is we are now taking the reason for the expansion under the log term of the log term. So we are considering the classical case. So we want to move out of the quantum region. So classical case, usually this happens at T is very large at higher temperatures. So if you consider this term here, this minus beta epsilon j minus mu, so beta is 1 over kBt, so this term becomes pretty small in the higher temperature region. So I mention here also that at higher temperatures, at high temperatures, this expansion becomes valid. So we are basically trying to study the high temperature approximation of our Bose Einstein statistics. So I stop it here because I need to calculate first the Bose Einstein distribution function, and then we can come back to this later. So first, as I said that we need to calculate this Bose Einstein distribution function. So let's go back to equation 2 here that we have here, and we calculate the grand potential from this. Grand potential and grand potential, we know that phi g is minus 1 over beta log of the grand partition function. That is the standard definition we have. And from this, if we put the value of log of z in this, we get 1 over beta the summation over j log of 1 minus beta epsilon j minus mu. This is our phi g, and if we want to now calculate our distribution function or particle occupancy, the Bose Einstein distribution function may now be calculated from this. That would be given by f of j, you can call it, or f of k, whatever index you want to use. So that would be minus of partial phi g over partial mu at constant temperature and volume. That is our standard formula, and if you use it, you will get f of j. So we denote it like this: average number of value, it's like 1 over e to the power beta epsilon j minus mu minus 1. This is our equation 4. So this gives us the probability distribution function f of j, and this is very important for us to know about this thing clearly. So if we see, this has very clear difference from the Fermi-Dirac distribution. So Fermi-Dirac distribution contained a plus sign here, and this Bose Einstein distribution function contains a minus sign here. So you should be really aware of these two symbols here. And another thing you need to remember, that for low temperatures, Fj is much greater than 1, while Nj or Ni that we had in case of our Fermi distribution, that was almost equal to 1 in case of low temperatures. So these are the two differentiating things between these two. Otherwise, we will have just to remember that one contains a plus sign here and one contains a minus sign here. So now, as I did in previously here in equation 3, that I wrote a high temperature limit or classical limit of our log of the partition function. So now I want to write the Bose Einstein distribution in the classical limit. So next what I do is, now we write Bose Einstein distribution function in the high temperature or classical limit. So for that, I need to rewrite equation 4 again. So I write f of k So I take this term common, and we are left with this thing here, and now this second term, as we already mentioned, that this term is really small than 1, the previous expansion is much smaller than 1, so we can ignore this, and what we are left with is, so in that limit this term is removed, so we are left with e to the power minus beta epsilon j minus mu. And if you see now that I have written CL along this, that means it's a classical Fermi-Dirac Bose Einstein distribution. Another thing to be remembered here is that whether it is Fermi-Dirac or Bose Einstein, so if you remove this term or ignore this term here, so you are left with same kind of approximation, whether it is Bose Einstein distribution function f of j, or you have the Fermi-Dirac distribution n of j that we studied in the last lecture. So the classical shape of both of these distributions is the same. It's like this. We don't need to write separate Bose Einstein and Fermi-Dirac. So it's a one function for classical case. And now it's easier for us to estimate other things from in the classical region from these functions. So I go back to equation, our equation for the classical partition function, that is equation 3. I go back to equation 3. Okay, first I call this equation our equation, next equation is our equation 5. This is our equation 5 now, and I have to go back or reconsider the case of equation 3, reconsider equation 3, that is our partition function in the classical case, that is log of z equals summation over j e to the power minus beta epsilon j minus mu. And now we have to do two modifications. First, we consider a free boson gas, for which we should write Ej equals h cut square k square over 2m. So it बोसॉन गैस है और उसमें ईच पार्टिकल का मास m है, ऑफ पार्टिकल्स each with mass m. That is the first case I said that we gonna study. And now we also have to, because we are somehow changed from our discrete to continuum, so we are now in continuum case space, so we have to change this summation to an integral, and you know the procedure, we did it a couple of times before. So we change the integral, the summation to an integral in K space. You know the procedure really well. So what we do, we simply transfer this summation and we write gamma v over 2 pi cube integral over K space d cube k and e to the power minus beta h cut square k square over 2m. That is our conversion that at the end of the day we have to do to convert this log of z to the K space and do some integrations. And now you also know, we discussed even in the last lecture, that d cube k is the volume element in K space, and that is 4 pi k square dk. Then we just replace it. So our log of the grand partition function is gamma. Gamma is familiar to you. This is called spin multiplicity. We discussed this in the last lecture. Gamma v over 2 pi cube. Remember, v is the volume of the sphere in real space. So we write it times 4 pi k square e to the power minus beta k square h cut square over 2m dk. So the limits of integration are minus infinity to plus infinity. They have to integrate over so okay, I missed the new term here. I should write it back. So keep on modifying. So this is gamma times v times 4 pi over 2 pi cube, and we can take the term containing mu, so that is e to the power beta mu out of the integral. So that is now we are only left with the terms which are dependent upon k. And now we have to do some replacements, and we can simply integrate this function. So if we put substitution, so if we let's do some substitution, simple substitution to solve this integration. So simple substitution is we put x square equal to everything that is on the exponential, on the power of exponential, beta h cut k square over 2m. This thing we let it x square. So our k square would be then 2m over beta h cut square times x square, and our dk will be 2m over beta h cut square root dx. So if we put these things inside this integral, what we gonna get? We get log of the partition function is 4 pi over 2 pi cube gamma e to the power beta mu 2m over beta h cut square 3/2 integral of minus infinity to plus infinity x square e to the power minus x square dx. And this integral, we have a solution for it. So this integral is precisely equal to square root of pi over 2 you can check this integral, or you can do the explicit integration for this. So this you will get, and after all the manipulations you will end up getting log of the partition function simplified form. In the simplified form you get 2 over 2 pi cubed gamma e to the power beta mu times 2 pi m over beta h cut squared raised to the power 3/2. This is your final result for this. We call this equation 6. So I have mentioned that this is log of partition function CL, classical one, and from this classical we can calculate the classical partition classical potential, classical grand potential, that is now simple to write. That should be equal to minus 1 over beta log of C classical, and if we put up the values of log of ZCL, we get minus 2 gamma V over 2 pi cubed and 1 over beta raised to the power 5/2 and 2 pi m over h cut squared whole raised to the power 3/2 e to the power beta mu. This is our equation 7. This is our grand partition function in the classical case. Remember that. And now I introduce you to another term. Let's introduce fugacity. Fugacity is given by small z, that is e to the power beta mu, that is lying here. So we call this term fugacity. Fugacity is really important. We will discuss its important later, but for the time being we just use it as such. So first we write equation 6 in terms of fugacity. Let's rewrite. Equation 6 in terms of fugacity z. So what we get, log of classical z equals 2 gamma v over 2 pi cubed 2 pi m over beta h cut squared, everything raised to the power 3/2 times z. And what is the advantage of writing in terms of z? Okay, we can call this equation or equation 8. The advantage is now we can calculate the thermodynamic number of particles, total number of particles. Now the thermodynamic number of particles are calculated using the formula. We call it like this: an average. This is that would now be given by, in terms of fugacity, as z times partial over partial z log of c. And this is our classical case, so I write the term classical here. So at the end, when we put the values, we get the same expression like 8, but this time we call it n. That is 2 gamma v over 2 pi cubed 2 pi m over beta h cut square raised to the power 3/2 times z. And now we just rearrange the terms. So we write it, we separate the fugacity terms on one side, so we, on the other side, we get n over v times beta h cut square over 2 pi m raised to the power 3/2 8 pi cubed. So we have separated the terms containing fugacity, and now we can take log on both sides, natural log on both sides. So what we get beta mu equals natural log of n over v plus log of one over gamma h cut square over m k b raised to the power 3/2 and pi over 2 raised to the power 1/2 minus 3/2 log of t. So this is the final form we will get. Beta mu equals log of n over v log of 1 over gamma h cut square over m k b 3/2 pi by 2 raised to the power 1/2 minus 3/2 log of t. So So we can write it like this also: mu over k pt equals log of n over v plus log of some h cut square over gamma m k p 3/2 pi by 2 1/2 minus 3/2 log of t. And this is a very important relationship because it will give us this relationship. I call it equation 9 if I am right in enumeration. Last equation was equation 8. So this equation 9 is very important. It will give us the dependence of mu for the Bose gas, for the bosons or fermions, whatever the case may be, in the high temperature limit and if we plot this actually on the graph, you will clearly see what is going on high temperatures. If you plot a graph between temperature and mu using equation 9, this is your assignment now. So this will give us to plot mu versus t and see the behavior at higher t and if you can plot it, then you will remember how mu varies at high temperatures, what is its value, and this is your assignment before our next lecture. I hope you will be able to do it carefully and successfully, and once you do it during the next lecture we will study about the behavior of mu. If we don't take the classical limit, we take the original limit of original Fermi-Dirac distribution or Bose Einstein distribution, and you see if this differs from their behavior at high temperature and behavior at low temperature. Even you will see that okay, so they show one graph at higher temperatures, but they have totally different behaviors at low temperatures. In the next lecture, we will discuss specifically the behavior of free Bose gas, and we will introduce the concept of Bose Einstein condensation, what that means, taking mu into account. So we will introduce for next lecture we will introduce the concept of Bose Einstein condensation, and we will see what condensation means, and we will discuss in context to the liquid helium, superfluid helium, and we will discuss the analogies between superfluid helium and Bose Einstein condensate, and we will see how they are how they resemble and how they somehow differ from one another, and that would be really interesting topic for the next couple of lectures. And we will discuss also the behavior of this exponential function, that is e to the power beta E minus mu. So this function will be pretty crucial in discussing these type of behaviors, this exponential function. So your reading assignment is to read a little bit about from maybe Wikipedia the Bose Einstein condensation and superfluid helium, and we will discuss this during the next lecture. Superfluidity and liquid helium near absolute zero, like at minus 270 degree Kelvin. You need to do this reading assignment, and your actual assignment is to plot equation 9 and see how it goes. You can give me a schematic plot if you wish. So see you until the next lecture. Bye.